Thanks, Matt. Welcome to the PSI seminar here today on April 15. I'm pleased to welcome Erik Asphaug, who's going to talk with us about his work called After the Giant Impact. So, Erik, take it away.
All right.
Thanks for being here.
Oh yeah, thanks. It's a lot of fun to see everybody online and get a chance to sort of talk about a few of the things that I've been working on in the last couple of years and then have a new grant to focus on. So that's always fun. So whenever I show this, I have to distinguish this Don Davis from your Don Davis. This is a space artist Don Davis, who did, I think, the most beautiful and scientifically accurate painting at the time. This was back in the early 90s before supercomputer modeling. And I'll show you some supercomputer simulations later. And he caught, for instance, the shock wave. You can see it's starting to rip across the Earth. And in fact, if you're astute, you'll see the shock wave has yet to converge up at the top of Theia. So if you were standing at the top of Theia, you wouldn't have felt anything at this point, just due to the time it takes for you would have seen a lot, but you wouldn't have felt anything yet. Anyway, see if I can get going here. So I've got two topics, and so I'm going to go kind of fast because I think we are all quite familiar with the moon formation story to some extent. And I'm going to talk about other scenarios for giant impacts, including around, well, with smaller objects like Pluto, Charon, and then also for giant impacts around giant planets. So, uh, giant impacts that could have formed Titan is something I've been working on. So, there's lots of cases of, next sized objects looming in front of bigger objects in the solar system. And if you look at the Hartman and Davis paper from 1974, that was sort of the origin of the giant impact hypothesis was in that framework, 52 years ago now, it was that look, not everything's going to come in the form of tiny asteroids. You might have a power law distribution of sizes, and that might include really much bigger things. Um, Prior to the space age, there were all these ideas around moon formation. I was lucky enough to get into the field when some of these were still on the table. It was kind of being mopped up with the giant impact theory, but there was still a lot of thought about co-accretion. You can see this paper in 2001 was still looking at, how you could possibly get the job done. And now, as we'll talk about in a moment, people are starting to like revisit some of these early ideas because the giant impact hypothesis is in trouble. Um, Despite all the evidence, there's no shortage of evidence for a igneous moon, very dry. A giant impact could have driven away volatiles. It has a tiny iron core, which I think is the hardest thing to resolve without a giant impact, to accrete something that only has 4% or less uh, metallic iron. But without getting a lot into lunar geology, I just wanted to talk about the framework of giant impacts and the kind of trouble we're in right now. So we're getting a better idea of when the moon formed, and there's different opinions about that. 60, 30, 100, 140 million years are in current papers. It's starting to converge around this 100 million year post CAI formation time. A global remelting epoch a few hundred million years later, based on the late lunar zircons. I don't think I'll get into that at all, but there's some ideas related to that that have to do with post-giant impact processes. And then when it formed, it was only about five or so Earth radii away from the Earth in the giant impact models, typically around three. And so the tidal evolution would be enormously powerful and rapid. And as I'm going to talk about, the moon would be born deep in Earth's gravity well, which creates a certain danger for it. Um, I got a couple of movies in here. I just pulled some from different co-author or different authors who work on this just to show that a lot of people have their computers running. The early days of supercomputer modeling, sort of theoretical modeling at the top, and then supercomputer modeling introduced by Willie Bentz. and a lot of the analytical work about what the thermodynamics of this process might look like by Dave Stevenson, this seminal review chapter. Um, it explains everything that you wanted to explain: a silicate moon, globally melted, tiny iron core, the high Earth moon angular momentum. Uh, and so the this talk will take kind of two little paths here. On the one hand, we're at the advent of billion particle simulations. Back in the day of Willie Benz in 1986, the first moon formation models had 3,000 particles total, which means that the moon ended up with, the protolunar disk ended up with, a few dozen. And so one of the reasons why we were sort of led astray from the giant impact hypothesis back in the early to mid 90s was that the resolution was too low. And if you got a single SPH particle in that disk that was made of iron, that was too much. But we all know that these computer codes are approximations to reality. But this is the model by Jacob Kegereis et al. That came out in 2022. I think it's the science result, certainly the science moon forming simulation result that has the most clicks on YouTube. It's got like 2 million clicks and it's beautiful. Um, you can see that the giant impact, it's called a hit and it's called a graze and merge collision because it grazes and then it comes back and merges, and there's angular momentum exchanges that weren't really appreciated in the mid 90s, mid 80s, early 90s. That these angular momentum exchanges, that's what captures the moon in orbit, is the non-central gravity field of this whole process. The problem is that as amazing as this looks, and there's your moon sitting there, Jacob or Thomas Meyer and colleagues at University of Zurich uh, did the exact same simulation, almost the same resolution, same physics, same equation of state, and they get a completely different result. They don't get this big blob of a moon, they just get a debris disk. So,
Hey, Erik,
oh yeah.
I'm going to interrupt you real quick. I think that your slides are looking slightly cropped all around, and I don't want us to miss
Well,
anything. And I'm not sure if there's anything you can do on your end.
let's
Um,
see
I don't
here.
know if you're sort of zoomed in or something,
Let me try.
or
Not,
what.
not zoomed in. Do you see like the word figure on the left and the word 2022 on the right?
I don't see 20. Oh,
Okay.
now, no, now we're just looking at your PowerPoint. And it's like you're not presenting anymore.
Well, I'm not
But
presenting anymore. Let me try. Let me
you're
just,
not in slideshow mode.
oh gosh. Don't you
But
love?
you were.
Yeah, I'm just going to try again and see if
Okay.
helps. So how did this?
So push slideshow again, please.
Okay, let's see.
Because it didn't take.
Gosh, I'm in slide on my screen. I'm in slideshow mode.
Oh, so maybe it's something about like,
You're probably not sharing the right window, I'd guess.
Oh, do you think I have to go into presenter mode first and then click share?
I would do that. I would stop sharing
ah,
real quick
Okay,
okay.
let's do that.
and
Stop.
then yeah, now put it into present slideshow mode.
Okay.
And now when you go to share, make sure you're sharing the window that your slideshow is appearing in.
Okay, let's see. Oh yeah, here we go. How's
Oh,
that?
that's much better.
Oh, super
Yeah.
duper. Okay, great. Uh, yeah, I don't think you missed much. Origin of the
Okay.
Moon.
Yep,
Uh,
yep, yep.
and then you've got
Great.
this fabulous movie that you can all go look up on YouTube. If you type in moon formation, this is the first thing. And the point is that even at a billion particle type resolution, we can't trust. When I say we can't trust the answer, you have to recognize that the moon is 1% of the mass of the Earth-Moon system. And uh, if you were doing an impact cratering calculation, you're trying to figure out sort of the target and this big bulk of material, and you're not trusting the 1% of stuff that's going way down range. And here, that's the whole nature of the problem, is this little bead that's orbiting the Earth at the end. So it's a really hard problem. And then At the same time, we have this isotopic problem, isotopic crisis, as Jay Milosh called it. The moon is made mostly of Theia in the standard model, and all these isotopes are extremely Earth-like in composition. And I won't dwell on this because this is an old story, except I thought it was interesting that Paolo Sassi and his group put out a paper. I think Torsten Kleine was on this as well, that, framing the hypothesis maybe there wasn't a giant impact. And I talked to Sassi about this, and it's an important paper to have out there. Like maybe the isotopic similarity is just too great to have anything work. So I'm a giant impact believer, for better or worse. And so you've ended up with this array of models. Here's one pursued by Cameron in 2000, Canup in 2012, Nakajima and Stevenson, where you have two identical half Earths that hit, and then everything's symmetric. And so the moon's made 50-50, the Earth's made 50-50, everything's 50-50. The problem is the tiniest little asymmetry when you're trying to get a 1% bead to form out here that's moon material. You end up mostly making it out of one or the other. So I've been updating this chart, and the lumberyard of models, that's a quote from Harold Jeffries. I think he was talking about the lumberyard of hypotheses in need of a spring cleaning and a bonfire. And the truth is one of these is right. And so, but they just keep multiplying. And you go from the standard model where Theia is identical to Earth isotopically and was just sort of in a holding zone, maybe at a L4, L5 place around the sun. You could have diffusion of compositionally, but that theory kind of fell apart. Um, you could hide the composition of the moon under Earth equilibrated material that plasters onto the moon later. You could have a hit and run collision where Theia doesn't leave any of its imprint and it keeps going, but that doesn't quite work because it still mixes a lot of Theia in. Um, you could have a pure ice Theia, but I don't think you're going to have pure ice bodies of that size, and it's dynamically improbable to deliver them to the inner solar system late in Earth history, relatively late. You could have this 50-50 idea. You could have a super fast spinning proto-Earth. This is the Synestia model of Chuk and Stewart that has some. Yeah, the nice thing about this model is it's the only one that really solves the isotopic crisis because it just hits the big reset button and blows it all up and makes a nebula essentially from which the Earth and Moon then reaccrete locally. And there you have to have a fast spinning Earth. And so the problem is how do you get the Earth to be spinning like 10 times the rate it is today? Prior to the giant impact. So you have to have a giant impact spin it up and then another giant impact come in to do it. A series of giant impacts, one after the other by Raluca Rufu et al. And Odetta Harrison. Uh, and there you have the idea that you have multiple things. And the idea there is that you can have compositional diversity, but you have enough of them making the moon, you mix it all together. But that has some dynamical issues that you want them to be combined so that you don't deorbit the moon as you're making it. Impact into an already molten Earth. You give it a hot start, so you have a different impact physics, but then the Earth has to stay molten for late. You could have a collision chain. I'll return to this in a bit because we've been pumping on this idea for a while that you have multiple giant impacts by the same two bodies. And then you can have the slingshot that I just showed. And recently, Thomas Meyer and Adine Denton has in prep, but she's presenting it at JPGU, that strength actually matters at this scale. Friction makes a difference, especially in the formation of the moon. So what we need isn't more hypotheses. We don't need more supercomputer models just at higher resolution. What we really need is a deeper set of constraints. And I'm going to look at two of these. One is the constraint of debris sweep up after moon formation. And the idea here, and I'm just going to get my phone so I can keep track of time. The idea here of a sweep up is that when you make the moon, and this goes back to Alan Jackson, and I think there's a paper by Jackson and Wyatt in 2012 And there was a study by Marcus et al. In 2009 that looked at escape, what's the escaping fraction from a moon forming giant impact. And we've revisited this, and it's always about 1/2 to 1 lunar mass of stuff escapes. Even in the very slowest giant impact. I guess I haven't explained yet that the moon forming giant impact is one of the slowest that can be achieved because it depends on the acquisition of angular momentum of Theia to spin up the Earth and to fling out the moon. It's an angular momentum acquisition, therefore it's a mass acquisition. Therefore, it has to be a very slow collision. Faster collisions, as we'll see in a moment, lead to hit and runs where Theia keeps going. And it's a delicate tipping point. It's about 1.2 times the escape velocity that you start to get predominantly hit and run collisions. So it's not like you're in a fast regime. So for the canonical model, you make about 10 to 30 main belt asteroids of stuff, and it's all at 1 AU when you've made it. And that's going to be swept up in about 1 million years. And that's going to mostly come back to the Earth-Moon system. And so if you imagine the moon uh, newly formed, sitting there orbiting the Earth, being subject to this rather horrific bombardment, which hasn't been modeled yet, but it's going to be quite intensive. I have a student, Robert Malikian, looking into this. What is the possibility that you could deorbit the moon or bash apart its crust and change its composition uh, during this during this phase of returning debris? The more energetic your hypothesis, like synestias or multiple impacts or the hit and run return collision or the 50-50 semi-Earths, which has a huge amount of binding energy to get rid of, so it flings out a huge amount of debris. Uh, you're going to have 3, 4 times this much. So maybe 100 asteroid belts of material at 1 AU. And the question is, what would the signatures of that be, not just back on the Earth and Moon, but also locally on Venus and Mars and Mercury? Um, the other part is the early tidal evolution, and I'm not an expert on tides. People I know who are experts on tides, you talk to them and they tell you they don't really understand tides. So I think tides are somewhat of a um, uh, mysterious phenomenon in terms of how they relate to the internal structures of the planets. But generally speaking, if you had a very energetic giant impact making the moon, and you have a completely melted the Earth, you might have low Q, which implies slow tidal evolution, which then implies the moon is close to the Earth for a long period of time during the sweep up, making it more in danger of losing a significant fraction of its original mass. That's just an example. You could have a less energetic event that could leave a partially molten Earth that would have high tidal Q, and the moon could spin out really rapidly. So I'm not saying which of these happens, which is right. I'm just saying these are two independent ways of framing the hypothesis by looking at the corollary of the giant impact and not just looking at, these kind of two bodies in space. Instead, we're going to be looking at the long-term evolution of the stuff that escapes that's going to go off to the right of the screen. So that's the basic idea. You take these candidate hypotheses, you do dynamical evolutions of each collisional outcome. You look at the sweep up and bombardment in interplanetary space in the terrestrial region, and then you can maybe rule out some of these, right? If the moon gets clobbered by its own debris, you could maybe rule that out and then iterate. So that's kind of the framework of that idea. Uh, I think I can skip this. This is just, Zonley had this, he always called these toy models, but this is a nice graph of how the semi-major axis of the moon would change over time. And it hugs the Earth while the Earth is mostly, this was back in 2007 when it was thought the Earth would be just mostly liquid after the giant impact. And so it hugs the Earth because of the very low Q. And then once um, you know, partial crystallization of the Earth magma ocean occurs, then you start to have this ramping up of semi-major axis. And that matters to all the dynamical puzzles, like when did it cross the evection resonance where it could have lost angular momentum of the Earth-Moon system? When did it cross the Cassini plane? There's this Nimmo et al. Paper on possible remelting of the moon due to tidal activity 100 million years later. Uh, after its formation, but could the moon have taken 100 million years to get out to, I think it's 19 Earth radii? That's a long period of time for that to happen, requiring a very low Q of the Earth. That might require a cold start that left the Earth mostly solid. So there's independent constraints on this stuff. So getting into the more general problem here, mergers you see here on the bottom left, these are machine learned outcomes trained on a database of giant impacts. And the right is a scaling model based, also trained on giant impacts, but sort of divides it up into these domains. The main point, if you focus on the ones on the left, merger that makes the Earth-Moon system is at low collision velocity at an impact angle of around 45 degrees. So moon formation is kind of the letter Z in the bottom of this plot. Most collisions, if you start getting up to about 20–30% above the escape velocity, most collisions start to become hit and runs. And most of those are intact hit and runs, which you could think of it as a bounce, but it's a little bit different than a bounce. Now, one of the problems of making the moon out of Theia coming in so slow is that it constrains where Theia could be in the solar system. If you want Theia to be coming from, let's say, zero point 0.9 AU or zero point 0.8 AU, like in the pebble accretion theories of Johansen et al., where Theia and proto-Earth get born like a half an AU apart, you're going to have collision velocities that are much faster than this. And so hit and run should be about 50-50. And we have this database of all these things. And if I have time at the end, we can play with the database. But you dial in your slider between, 1/10,000th of an Earth mass and 5 Earth masses. You can have different impactor mass ratios. It's a nice way to build your intuition for things. And these all have strength. It doesn't matter super much for things when you start to get to moon forming sizes. But when we start to look at these giant impacts more generally, and we look at hit and run collisions, a typical slow giant impact, just to put this in context, you take the standard canonical model of the giant impact, increase its velocity by 10%, and that standard model is now a hit and run collision. So it doesn't take much to change an accretion to a hit and run collision. It's just the graze and merge, the grazer doesn't come back. It just keeps going. So what happens to the runner? And we had a series of papers, Alexandra Emsenhuber and I and colleagues, we had this fun series of papers, the fate of the runner or the collision chains trio of papers. And what happens to it? Well, most of the time you have a hit and run collision on the right here, and the runner comes back and you have a return collision. So about 60% of runners, Theia hit the Earth, keep going, they come back to the Earth, and you have a return collision. It's going to be slower. It's going to be pre-mixed. It's going to have already lost a lot of its silicates in the first collision, and the final collision is going to be inclined relative to the first one because there's very little memory of the initial event. So that's the basic framework of the hit and run return model of moon formation. It's a canonical model, but it has this backstory to it. And this is just, kind of the cartoon of it, proto-Earth, proto-Theia. They have a hit and run collision. Theia keeps going. You get to use the word Middle Earth in your paper. You have Theia already has some mixed component, and we tracked like the rate of mixing, and it helps. It doesn't solve the isotopic problem, but it gets you like halfway there, which doesn't get you there. But then you get a disk just like standard models. A lot of this stuff goes elsewhere. Here's the figure you just saw here on the left. Most of the stuff goes back to Earth. Some goes to Venus. Venus is asymmetric. Venus doesn't like to get rid of its runners. Venus likes to reaccrete its own runners. And so Earth, I won't dwell on this at all because it's a whole different talk, but there's this fundamental asymmetry between how Earth versus Venus would respond to a Theia-like impact. So jumping ahead, because in the interest of time, this is the grant that I got awarded it just turned on about a half a year ago or a little bit less. So we're just getting started on it. And this is giant impact origin of Titan. Um, we wrote about this in 2013, and then, as everybody does, you write a proposal, gets denied, you write another proposal, gets denied, and then you forget about it. But I find it quite intriguing. And in the final round of the second time we submitted it, they were like, this is all pretty cute, but you should really be, thinking about exomoons. And so we wrote a proposal that was kind of more exomoonish, but we talk about Titan, and that got selected. But the comments was, you guys really ought to be thinking about Titan. So, so anyway, we're thinking a lot about Titan, and it's odd. It mass is the sum of all the Galilean satellites relative to Jupiter. There's this constant satellite system mass relative to the giant planet. Maybe that's some sort of a constant of the universe. Who knows? I think Heller et al., I think, wrote a paper about how that might be. It might sort of always be like 10 to the minus 4 for giant planets. Um, it's on an eccentric orbit that has yet to be explained because it should be circularized within less than a billion years. Very active object, as you can see here, big, thick atmosphere. It's accompanied by weird middle-sized moons that I'll talk about in a second. And these are 300 kilometers to 1,500 kilometers diameter, Iapetus and Rhea and the big ones on the right, and things like Nemus and Hyperion on the left. And there's no correlation with size or distance of composition, which always befuddled me. And then Jupiter has none of these middle-sized moons, which also has befuddled me. And so here, Emily put together, Lakdawala put together this nice montage with the constant phase angle of the middle-sized moons compared to Titan. I put in their densities, icy, rocky, and you can see that they just bounce back and forth in silicate fraction versus distance. And you would expect if there was like some kind of a common disk origin, you would have a sort of a gradation of icy to rocky, maybe from interior or rocky to icy going outwards. Um, Theories abound. You have, Ignacio Mosquera et al. Proposed, had a model of accretion of the middle-sized moons directly in the nebula, which has a problem. They all have a problem with Iapetus, right? Iapetus is at 60 Saturn radii, almost pure ice, almost half the size of the moon. That's a very difficult problem to figure out, although it might come up in the context of this talk. Then you have papers by Robin Canup and Sebastian Chernoz and Krita that you have a massive ice disk around Saturn that then accretes middle-sized moons. And you have to come up with some explanation for why they are so massive, because this accretion model forms smaller objects, so they have to kind of sub-accrete and grow and grow and grow. And why did they end up being so diverse in composition? Sakina and Ganda had a very creative hypothesis that Proto-Rhea had a hit and run collision with a sibling to Titan at 5 Saturn radii that went spiraling in, and then you made the middle-sized moons by ripping apart Proto-Rhea. And we were working about the same time on this giant impact accretion of Titan. I won't show that simulation yet, but just think very much like moon formation. Theia, Titan's Theia, maybe something like Enceladus, I mean, like Europa, hits Proto-Titan, which might be like half the mass of Ganymede, and spawns off a moon, spawns off a disk, and a lot of that stuff would form a moon. But if you're in the tidal field of Saturn, if you're in the gravitational field of Saturn, you can't have stable moons of moons, and so they either crash back or they escape. Not much dynamics in this paper. It was all SPH based. Like we said, hey, we can make this, and I'll show you the results in a moment. And then Matya,
Eric, I'm sorry. Can you just go back to that real quick? Are you forming Titan through that, or are you forming the other moons from an impact on Titan?
we're forming Titan and the middle-sized moons.
Okay.
And
From an
Titan,
impact with Saturn?
no, an impact where you have very similar to Theia and Proto-Earth. Here you have Theia and Proto-Titan.
Okay. So
And
you already had a Titan there. So
Exactly.
it's not forming Titan.
Exactly.
Okay.
You're bringing in like the last
Okay.
30% of Titan's
Got it.
mass.
Got it. Okay. Thank you.
And then you spin off these miscreants in the process.
Okay. Thanks.
I appreciate the question. And anybody else, if you want to have questions as I go, because I'm blasting through. Um, oh yeah, and then there was this, the Daily Mail picked up on it as like Saturn's moons may be younger than the dinosaurs, and there's a lot of work, and it's really hard to keep up with all the theories. But there is this sense of, something happened 100 million years ago. I'm not saying this happened 100 million years ago, but the Saturn system does have, when I was in grad school, all the planets were finished a long time ago, and now we're here to just kind of observe them evolving. And this idea that planet formation might be occurring late into solar system history is quite interesting. So we set up the model as a bunch of proto-titans. So here they are. And we don't know, and we don't have a good equation of state for serpentine that that would work with these. And so uh, we just have a small metal core, rocky mantle, icy exterior. We set it up in you know, a consistent model with pressure, temperature, density, and then you get the um, evolution of the uh, that's your initial target for the collision. And then here's the collision. And what's unique about this is we've put it in the gravity field of Saturn. And the gravity field of Saturn is intense when you're orbiting around 10 Saturn radii. That's where these are at. And instead of it being a two-body system, you've got this huge third body off to the right in the left frame, and you're looking from Saturn on the right-hand frame, and or no, you're looking from Saturn in the left-hand frame, and you're trailing them in their orbit in the right-hand frame. And I'll just play it and see if you can make sense of it. Let's see if it's going. Here we go. It's not playing. There we go. It keeps stopping. Are you guys seeing that as a movie?
I was, but it stopped.
Yeah, let me try. Let me try going back again. Here we go. And so you can see the Coriolis effect. The collision takes about, um, by the time you've had three or four of these graze and merge kind of things, that's been going on for maybe 2 or 3 days. That's about a quarter of, well, at 10 Saturn radii, this would be most of Titan's orbit around Saturn. So the point is, what would have been kind of a nice little graze and merge collision is now a graze and graze and graze and graze collision. And every one of those little things that go beating off there, those are about 300 to 1,000 kilometer diameter blobs. And if you look in detail at those blobs, and so here you get a static view of the uh, changing orientation of this three body, well, now multiple body system. What's interesting when you start to look at what these things are made of, so here we picked a simulation that had an icy thing, kind of rocky thing, icy, 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 little rocky core. The little circle is the rock, and the rest is ice. Uh, you can play with these, of course, and get kind of different things that you want, but we thought this was kind of cute because we had a big icy thing that we'd say that's Tethys, a littler thing that has a big rocky core, we'd say that's Enceladus, that's Rhea, etc. Uh, the real point, not, it's a danger to believe your models, but they indicate phenomena. And one of these phenomena is that Tethys, the blue guy, comes from the icy mantle. Enceladus, the brown guy, comes from deeper near the core of, Theia in the Saturn system. And so that would explain how you have some things rocky, some things. And what's interesting is the pressure unloading as you go from being snug as a bug in this, 3,000 kilometer diameter body. Now you're in a 500-kilometer diameter body. Your pressure drops by like two orders of magnitude, and that releases, now you're under pressure. And so this notion of Enceladus being a metastable body emerged from this paper. This just kind of shows it a little bit better, but I'll skip that for now. So wrapping up, coming on the home stretch, Pluto and Charon. The reason I'm showing this is that we started to put strength in these models, and we're going to be using strength in all of our simulations from now on, because without strength, the Pluto Charon giant impact simulations, you could form Charon in this manner, but it was kind of an extraordinary accomplishment. You have to have uh, the proto Charon being several times more massive than Charon, counter rotating so that any of it survives as a clump, and then it gets kind of impacted and tidally shredded. And then in the end, you end up with something about the size of Charon, but it's on a highly elliptical orbit. And so that was Canup 2012, I think. And what we did, and this is work published by Adine Denton now, was looked at the same simulation with strength. And what was kind of cool, if I can get this movie to work, I'm going to try the same trick again. All right, here it comes. And there's a lot of dissipation because of friction. Let me try this again. Wow, you might not get to the punchline. Let's see. Okay, there it goes. And it sticks, but there's tidal dissipation going on, even though it's stuck. And wow, it's like it doesn't want to go past this point. Come on, you can do it. I've never had this problem before where my movie just stops.
I wonder if you turn off your video, Erik, momentarily anyway. Oh,
It gets to like there. Oh yeah, that's a good idea. Let me try that. Uh, oh, but then I think I'd have to get out of full screen mode. Let me give it one
I turned
last.
your video off, Erik.
Oh, okay, there we go. Oh yeah, so now you see that it's stuck. It's spinning off stuff, and then tides are still happening, but the tides are gradual, and so it gets this initial circular orbit, and then it's permanently captured from the start. And then it's going to start evolving outwards because Pluto's spinning faster. And so this is this idea. You have this big debris disk, Pluto Charon, and then now begins the next phase of the game is to try to get those things where they are. So that is the end of my talk. I am working on this from a NASA Emerging Worlds grant on giant impact of moons of giant planets. I'm working with Robert Malikian, who's got a finest to work on this moon formation ideas. And then the diversity and geophysics of the largest asteroids I didn't touch on, but that's part of the Psyche mission for NASA Discovery. So I'm going to park it there to leave time for questions.
okay, awesome. Thank you so much, Erik. This is really fascinating stuff that you're working on. Appreciate you taking the time. Um, where'd you go, Erik? Can you turn your video back on?
Oh
I
yeah,
can
let's
see you.
see. Here we go. Uh,
Okay.
oh, I think you guys have to.
Maybe Matt needs to do it. But in the meantime, folks out there, raise your hand for questions. Herbie Runyon.
Yeah, really interesting talk. Thanks, Eric. And I'm not a modeler. I'm a geomorphologist and a mapper. And so this is a little naive, but I guess just the simpler capture model has been completely disproven. And the only reason I say that is because I know Jack Schmidt brings it up at every lunar conference or something.
For the moon. For the
For
moon.
the moon, yeah, for Earth's
Yep.
moon.
Well, yeah, but
I,
it gives Jack Schmidt an opportunity to pick up the mic and say, when I was walking on the moon.
yeah, we can't say that. When I was running my impact model. Um, but I think we've entered the era, I think now, of collisional capture. It's like it is capture, but you have to stop it
Mm,
by hitting the earth.
Okay.
Yeah.
okay. Okay, let's see. Hannah's got a question in the chat. The moon formation section of the talk prompted this question: do we have any independent constraints on the timing of the moon forming impact versus the impact that caused Venus's slow backward rotation?
Hmm.
Could something like one of the riders you talked about have been responsible for both?
Well, if you live in the world of pebble accretion theory and you think there were, a few, like maybe, well, I don't know if you're familiar with the Johansen et al. 2020 paper of, boom, 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 you make all the terrestrial planets in a row, and then you get Theia and you get the Earth. And so you get he's like, I'll give you one giant impact because I think they realize you need one giant impact to make the moon. Um, then you could imagine these scenarios where you hit the Earth, and then it goes on to hit the moon, or hit Venus, that kind of thing. If you're in the other camp of late stage accretion, then there were dozens of these things leading up to Earth formation. Um, I think that the timing I mean, that kind of gets to this idea of debris going from place to place, because one thing I didn't mention was that when you make the moon at the Earth, Venus is going to accrete about 10 to 20 kilometers thick new material post moon formation giant impact, just from the debris that got sent out, regardless of whether it comes in big chunks or
Mhm.
dust or whatever. Like one lunar mass of material split pretty much 50-50 between Earth and Venus is what happens to it in most of these scenarios. Venus should get resurfaced to a depth of 10 kilometers or so. Whether that could explain Venus is, a completely other question. But those are the kind of connections I'm hoping we might find by the end of this project.
See, Nolan, do you have a question?
Yes. Actually, Eric, this is a physics question. For most of these simulations, I noticed there is a thread of materials. Uh,
Hmm.
and what differentiate the particles at one point in the thread versus further out, for example? Is it the velocity or what is the physics behind?
Like, why do you get this chain of
Yeah,
stuff, strand?
yeah.
Um, it's a really great question. We call it walking the dog because you have this epic where there's this big strand connecting Earth and
Mm,
Theia during the Grays and Merge collision. I mean, it's sort of a tubular instability. It's very similar in some ways to like galaxy collisions and things where you get strands and arms. I think it's fundamentally an instability, gravitational instability in a cylinder as you pull it apart. But the only thing I can really say about that is that we looked at the spacings of, eventually that strand
Mhm.
gets pulled into clumps. And what's the clump size? There's a Chandrasekhar actually derived this for an infinite cylinder of constant density. And it turns out that for an infinite cylinder of constant density, the gravitational instability spacing is about equal to the cylinder diameter. to within about 8%, I think. It's a little bit bigger than the cylinder diameter. And so we just sort of saw that the beads are forming at about that spacing, but we haven't looked into it in any further detail than that.
Okay, thanks.
Who else has questions for Erik? Okay, I have a question that will demonstrate how little I've been following the field. But I got to thinking about the impact rate on the moon with the Artemis, flashes that we're seeing and everything in the flyby. And I think that the fact that those astronauts saw 5 or 6 impact flashes gives us a good kind of baseline for the current impact rate on the moon for small impacts. Is the thinking now, because again, I haven't been tracking this, that those impactors are all necessarily products of impacts from completely elsewhere in the solar system, like in the asteroid belt? Or is any of that material left over from the giant impact and collisional formation of the moon?
I think that what escapes the moon and comes back to the moon is that's kind of the big question. I don't know how much would be related to the giant impact, but there's a lot of evidence for asteroids with lunar,
Yeah.
increasing evidence of asteroids with lunar composition sticking around. And something like Tycho, uh, I think a long time ago people all would speculate, like, what if those rays keep going, right? And those rays do keep going. And Misha Kraslovsky had an interesting study where there are these sort of like radar rough stripes in different places on the moon. And we did a unpublished little study of like, I think it was Tycho ejecta would come back kind of in that alignment after orbiting the Earth a few times.
Okay.
So I do
Okay.
think you have a lot of like whenever you have a once in 1,000 year event on the moon, I
That
think.
material sticks around and is eventually going to hit again.
Yeah, and the kind of stuff
Yep.
that's making these 200 meter and smaller craters, those are currently unobservable, I think, for the most part.
Okay.
So my prediction would be that you're going to see a lot more like little lunar bits in the near Earth asteroid population.
Okay.
I,
Got
I
it.
if I had to guess, I'm getting into trouble here because I don't know. You put your ignorance on the table. I'll put mine on the table. Um, you know, what's the fraction of those that are lunar sourced impactors versus
Right.
native asteroids? And I'd say it's probably mostly more lunar.
Okay. Okay, great. Thanks. Herbie.
Yeah, I got another question. You mentioned in your recently selected grant, congratulations, that there's a component of it that's looking at exomoon capture. And so I guess I'm wondering, to my knowledge, we haven't discovered any exomoons. What are you using for any constraints? Or are you creating like this big library of like, hey, here's everything that's possible, maybe constrained on like what on the known exoplanet properties. But can you talk a little bit more about your exomoon research?
Yeah, that's a great question. I mean, I think we start with the things we know with Saturn and Jupiter, and they have moons. So Jupiter has one kind of moons, Saturn has another kind of moons. Jupiter has this resonant system, Saturn has this weird system. Which one is weird, which one's normal? And what we want to do is to look at, let's say, super Jupiters with Mars to Earth mass moons. Like you can imagine an Earth mass moon around a planet 10 times the mass of Jupiter, having a collision that would be exactly like moon formation in our solar system around the Earth, except that that thing would, probably, I think, be more like the middle-sized moons of Saturn. because you can't capture that stuff into an orbital ring around the target. It's going to be deep in the, the tidal field of the planet. So that's sort of the idea, is to look at what would giant impacts look like in around planets of arbitrary mass and disks of arbitrary mass and composition, and see if we can, on the one hand, come up with like an astrobiological vector here, because these bigger things are going to be more geologically active, and a lot of these things are closer to their stars. That it's not an astrobiology focused objective, but I think that's kind of on our mind, is can you have Earths orbiting superjupiters? Uh, what would happen if there is a destabilizing collision? So that's, but I think it's more of the latter end. Like we're going to just run a bunch of things and see the kind of landscape we get.
So how are you like the parameter space is infinite. How are you even just like constraining it? Are you constraining it to like super Jupiters and these conditions?
Yeah. We start with Jupiter and the system and just scale it up and down. And that's kind of the first cut. So to make the Titan in this model, you could scale the Jupiter system down by a factor of 3 in mass and scale everything down by a factor of 3 in mass, and just say, I'm gonna have mini Callisto hit mini Ganymede, and say, there's a disturbance in the force, and something happens to cause these things to become dynamically unstable and collide. Once you do have this kind of collision, then there are a couple of questions come to mind: is what's the survival of these things? Just because you make them doesn't mean they're going to stick around. They might re-impact and go away. And but yeah, right now it's really just starting with Jupiter and scaling it up and down, and then seeing what, take it from there, and then also play with composition. But yeah, I hear your point about the parameter space being infinite, and I think we're going to just try to have two slices through it,
Yeah,
composition and Jupiter-sized, Jupiter-like initial states.
very cool. Thanks.
Okay. Anybody else have a question for Erik? If not, I think we'll wrap it up there. Thank you again, Erik. We're going to get your slides and the presentation posted for others to watch who weren't able to make it today. And it's been really fascinating having you with us. Hang on. Bea.
Yeah, I don't know if that's allowed to ask a non-scientific question.
Please.
Okay, like, why do you want to join PSI?
Oh, that kind of question.
Yes.
Now, like, what's your favorite color? We just jumped to that one.
Well, that is blue. Let's see.
I mean, you don't have to answer if you don't want to, but I'm just curious.
Well, it's a way to keep, I'll be retiring at 65,
Okay. All right.
And it's a way to, just
To keep your fingers in the...
sail off into the sunset, right?
Good enough. Thanks.
Mm-hmm.
Okay, great. Well, thanks again, Erik.
Thanks for the opportunity. Great to see everybody's names. It's kind of neat to see the whole gang. Thanks, Jordy. How many people, and I might see a bunch of you guys at ACM, perhaps.
Yes. We should have a few people there.
That would be fun.
Okay, good. We'll talk to you later, Erik. Thanks again.
Bye.